Hello, this is Group 5 for AERO 421 Midterm Project. I'm Edgar Bustillos, and the topic that my group is going to present is image quality and nearest equation. So to start, what is image quality and nearest equation? So image quality can be defined as how well images can be used to extract information from them, and a common measuring scale for image quality is the National Imagery Interpretability Rating Scale, the NIRS. And this scale is used to rate images based on the interpretability of the images. So it rates images by how useful they are and not just by their resolution or how pretty they look. So this scale consists of 10 levels ranging from 0 to 9, where 0 means the image is not useful, you cannot obtain information from them, and 9 means the images have very fine details on them. So this means the nearest is a very subjective scale system because it's based on the amount of information that you can get from the images. And since the scale is very subjective, the general image quality equation was created to help engineers more objectively predict how sensors are going to perform.
Here is the NIIRS equation. It is made up of 5 distinct variables that are used to describe the image quality. The first variable is GSD, and it is the system ground sample distance. It represents the size of one image pixel on the ground. A smaller GSD usually means finer spatial detail and a higher NIIRS rating. The second variable, RER, is a system post-processing relative edge response. It describes how sharply edges appear in the image after processing. A higher RER means sharper edges and better object recognition. The third variable, G, is a system post-processing noise gain. It represents how much noise is amplified during image processing. A higher noise gain can reduce image quality. The fourth variable, SNR, is a signal-to-noise ratio of the unprocessed imagery. It compares the useful image signal to random noise. A higher SNR means a cleaner image and better interpretability. H is a system post-processing edge overshoot factor. It represents ringing or artificial edge enhancement caused by sharpening. Too much overshoot can make the image look sharper but less accurate. The equation changes slightly depending on whether RER is above or below 0.9. Since RER measures edge sharpness, this condition separates sharper images from images with weaker edge response. When RER is less than 0.9, edge sharpness has a stronger effect on the predicted NIRS value. Overall, the NIRS equation shows that the image interpretability depends on resolution, sharpness, noise, and processing artifacts, not just pixel size.
Sensors are rated on a subjective rating system. This system rates on how well an analyst can use the image to perform a task based on interpretability and quality. The system rating ranges from 0 to 9, where 0 is an image that has little to no usable interpretability, and a 9 is an image that is used in specific and detailed interpretation tasks. As rating increases, difficulty and details of a tasks an image can support increases. Here we have an image that can be graded and rated using the scale based on an analyst's own subjective opinion on how they can use it. Since different images can be interpreted for different tasks, there are 4 major types: visible, radar, infrared, and multispectral. Visible images are images of what the human eyes can see. Radar are images captured through radar signals where the visibility is blocked, such as in smoke and bad weather. Infrared are images detecting thermal energy. Multispectral is multi-wavelength data imaging. An example is from the Mars rover Perseverance, capturing images of Mars surface. An image capturing the general landscape would be rated lower compared to a high quality image detailing rock layers and surface texture. Here we have an image that would be graded higher since we can see a lot of details of the surface.
All right, so this entire time we've been talking about how NIRS is a image quality index. But what does that actually mean, and when is it important to have high quality imaging? Well, in English, the sort of qualities of an image or what makes an image good is broken down to two big ideas or umbrellas. One being how easy it is to tell what the image is, and one being whether or not there's things getting in the way of understanding what the image is. So, for the first one, that would be spatial resolution, sharpness and blur, signal to noise ratio, contrast, things like that, where it's just clarity of what the image is. And then the second one, image purity, is talking about are there obstructions in the way, like artifacting on the data that you captured, or are the viewing conditions poor? Is it in the shadow or overexposed? Are there other objects that are in the way of the thing that you're trying to depict? Those are all important. Now, when is having good image quality important, and why is it important? Well, it sort of depends on your use case. Often, it's most important when measuring things with fine details matters, or when an event is happening and may only happen once, or maybe you don't want it to happen multiple times and you're trying to capture data specific to that. A good example would be forest fires, where you don't want to repeat that, but having that high quality data is imperative. So, in general, you'll see a lot of high quality demands in defense industry for locating enemy encampments or any enemy technology. But it's also important in other applications like biosphere visual surveys or medical applications where seeing those fine details and diagnosing specific things is really important. So just for an example of what I was talking about earlier with the image quality, it's more than just resolution. There's things like edge sharpness, reduced contrast, and noise, which can by themselves either enhance or worsen the quality of an image.
So for spacecraft especially, there are a lot of sources of error, and there are mathematical tools that you can use to reduce that error, mitigate it. So for pointing error, you can convert the angular error that you have into pixel error. How big of an effect a slight deviation from the target angle will affect your image is based on the focal distance and pixel size inversely. So if you increase focal distance, there's going to be more of an effect. If you increase pixel size, there's going to be less of an effect on the image. And you can fix this with a separate system to control how the angle of the camera or sensor is positioned using something more accurate and quick than a reaction wheel for the actual spacecraft itself. So you'd have them acting in tandem, and the smaller, more accurate one would be, for example, a piezo stage or a fast steering mirror. You can see how that manipulates the beam either coming in or coming out. And so for blur and smear, you can use a Laplacian filter to select out the parts of the image that are changing the quickest and then sharpen them. You can see on the graph on the right how an object that you take a picture of, it might be blurry and you can sharpen that image. And then for smear specifically, that's based on how long the shutter is open for an image, and that translates with the velocity of the spacecraft to a certain amount of error. And you can reduce the exposure time, but that also decreases the signal to noise ratio, which is bad for low lighting or fast moving spacecraft optics. So using a time delay integral, you can take the average over a smeared frame and kind of reconstruct it based on how the pointing error has changed over that distance that you've traveled. And for wave field error correction, it's a bit more complicated. You have a bunch of different factors that you can decompose into Zernike modes. And these can include defocus aberration, included at the top, which is dependent on the distance that a spacecraft is from the target. And there are other sources of error as well, whether it's astigmatism or the angle of the lens or aberrations on the lens itself. And these can be analyzed, and then you can have a control system to correct them individually.
So just to summarize everything we've gone over, essentially NIRS is an image quality index that describes subjectively how much information you can extract from your imaging. There's a few variables at play that influence this number, and there's a few things that play into the quality of the image itself, such as artifacting and contrast and sharpness, those sorts of things. And there's also some factors like jitter, blur, and smear, or wave field error that can make your imaging poor. Luckily, there are some methods for mitigating these, some of which require more money, but some of which are pretty easy to implement. So yeah, thank you for watching, and happy imaging.